Have you ever really stopped to think about what gives your soda that fizz? Or, what's happening inside your own body to keep everything in perfect balance? Well, the answer is this kind of hidden chemical superpower, and it all belongs to something we call a weak acid.
That's a really great question, right? I mean, they're both acids. So what makes one a tasty salad dressing and the other something you definitely don't want to mess with? The answer isn't just about strength in the way we usually think of it. It's about a really fascinating difference in their chemical personalities. Okay, so to figure this out, we've got to start with a basic definition. At their very core, all acids do one thing. They are ion donors. The moment they hit water, they release, or donate, these little positively charged particles called hydrogen ions.
And right there, in that simple act of donating, is where the whole story is. See, the real difference between a so-called strong acid and a weak one isn't about how dangerous it is. It's really all about generosity. It comes down to how willing they are to actually give away those hydrogen ions. Here's a great way to think about it. A strong acid, it's like a glass bottle hitting a concrete floor. It just shatters, completely, irreversibly. It releases everything it has all at once. But a weak acid, well, that's more like a piggy bank. You can shake it, and sure, a few coins, or in this case, ions, will fall out, but most of them stay safely tucked inside.
So in the world of chemistry, that shattering bottle is what we call a one-way reaction. Once those hydrogen ions break off from the main molecule, that's it. Game over. There is no going back. The reaction is final. But our weak acid, our little piggy bank, is completely different. It's a two-way street. A few ions break away, yeah, but they can also just snap right back onto their original molecule. It's this constant back-and-forth dance happening all the time. So this two-way street, what does that actually mean for the acid itself? Because this idea is one of the most powerful and important concepts in all of chemistry. So let's break it down. It's a state we call chemical equilibrium. Now here's the key thing you've got to get about equilibrium. It does not mean everything has stopped. Not at all. It means the molecules are breaking apart at the exact same speed that the ions are getting back together. And what you get is this incredible system that's both dynamic and completely stable. At any given moment, most of the acid is still whole, just hanging out as complete molecules, with only a small but constant group of ions floating around freely. It's a perfect, self-regulating balance. And you know how chemists show this? With this symbol right here. Whenever you see this double arrow in a chemical equation, it's a huge signal. It's basically shouting at you that we're not on a one-way street anymore. We're looking at a reversible reaction that finds that perfect balance. It is the signature of a weak acid. Okay, so if weak acids only let go of some of their ions, that kind of brings up a question, doesn't it? Are they all equally weak? How do we compare the acid in our vinegar to the acid that makes our soda fizz? We need a way to measure this tendency to hold on. We need a number. And for something like vinegar, this is the number that tells its story. I know, it's tiny, right? What could that possibly tell us? It looks like almost nothing, but believe it or not, that tiny number tells us everything we need to know about an acid's personality. Well, that number has a name. It's called the acid dissociation constant, or just Ka for short. It's a super precise measurement of where that equilibrium point lies. And the rule is really simple. The smaller the Ka value, the less the acid breaks apart, and therefore, the weaker it is.
And this is where it gets really fun. We can use Ka to compare acids we run into all the time. So acetic acid, that's vinegar, has a Ka of about 10 to the minus 5. But look at carbonic acid, the stuff that makes your soda fizzy. Its Ka is way down at 10 to the minus 7. That's 100 times smaller, which means carbonic acid is even weaker than vinegar. It holds onto its ions way more tightly. And looking at it this way, it makes it crystal clear, doesn't it? You can see there's a whole spectrum of strength even inside this weak category. Carbonic acid is the weakest of this group, while formic acid, the stuff that's in ant stings, by the way, is the strongest of these weak acids because it has the biggest Ka value. It lets go of its ions just a little bit more easily. So here's the big takeaway. We've got to change how we think about that word weak. In chemistry, it doesn't mean powerless or useless. It means controlled. It means in balance. And this amazing ability to exist in a stable, reversible equilibrium, that's its chemical superpower.
Okay, so why does any of this actually matter outside of a chemistry lab? Why is this balance, this so-called weakness, so incredibly important in our day-to-day world? Oh, they are literally everywhere. That controlled release of ions from acetic acid is exactly what makes vinegar a great food preservative. The delicate equilibrium of carbonic acid is what gives us fizzy drinks. And maybe most important of all, weak acids act as buffers in our blood, keeping its pH at the precise level we need to, live. They're even in our medicines, like aspirin.
So let's bring it all home. The essential difference isn't really about danger versus safety, it's about control. Strong acids are like an explosion, an all or nothing reaction. But weak acids, they are the masters of balance, using their controlled, reversible equilibrium to become some of the most useful and important chemicals in our world.
So that's the superpower. It's not about brute force, it's about maintaining a perfect dynamic balance. Now that you understand the power of equilibrium, I bet you'll start seeing it everywhere, and not just in chemistry. So, what else in your world do you think is secretly being governed by this constant, invisible dance? Thanks for watching.